Last day, I talked about voltage, and I have to be honest, voltage is an incredibly tricky concept to figure out. So here is the question. If you touch the terminals of a 100-volt battery, or even a 12-volt car battery, you're going to get a good shock. However, if you touch a 10,000-volt rubber balloon, you don't get a shock at all. Why?
Rubber's not conductive.
Nope. It's not nothing to do with rubber being not conductive. Good guess, but no. And I'm glad you guessed that. That's one of the first things kids guess, and it's a fundamental misconception of how voltage works. Why is it that if you touch, or even, I'll even go more specific, if you take a little 9-volt, one of those rectangular batteries, and you touch it to your tongue, you feel a shock. But if you rub a balloon on your hair, you can get tens of thousands of volts and feel no shock. Why? So this is what we're going to talk about today and for the next few days. It has to do with how voltage is defined. Who can remember, how did we define what voltage was? And if not, you might want to go back and look in your notes. You're also going to want your formula sheet out again today. You'll be getting another equation today, and it's important that you look where they all are so that you can piece them together. What was voltage? It was also called electric potential, but what was it? How did I define it? I think you can find its definition as an actual equation on your formula sheet, and then rather than reading the equation, replace it with the English words and tell me how we defined it. How did we define voltage? Newtons per coulomb was electric field. It was something per coulomb. How do you know it's joules per coulomb? Look at your formula sheet. Isn't it one of the equations for voltage? Doesn't it say V equals, or change in voltage equals change in EP over, okay. Voltage is how much energy each coulomb of charge has. Let me say that again, this is hugely important. Rather than voltage is how much energy each coulomb of charge has. The reason you don't get a shock from a balloon, even though it's got 10,000 volts, it doesn't have very much charge. There's not many coulombs. The reason you get a shock from a battery is because even though each charge doesn't have much energy, there's trillions of charges. You know what? Here is your analogy, and this is what we're going to take to the bank. Courtney, to wrap your brain around voltage, you can sort of, and this is not a perfect analogy, but it's pretty good, you can sort of think of voltage as height. If a single drop of rain hits you from a height of 10,000 meters, we would say that that rain has a lot of voltage, but because there's so few molecules, so few coulombs, when it hits you in the head, you would hardly notice it, even though you've just absorbed 10,000 meters of potential energy, 10,000 volts. Compare that with, suppose ceiling high, we had a swimming pool right there, and the entire swimming pool dropped down on you. Each molecule of water would not have much voltage, would not have much height, but because there's so many more molecules of water, it's going to do damage. It's going to do damage. Voltage tells you how much energy per coulomb. Doesn't tell you how much energy you're going to absorb, because you need to know how many coulombs there are as a source. So a balloon, because it's not conductive, doesn't build up much of a charge, but each charge can get an awful lot of energy. You can get up to 10, 20, 30. In fact, most of you have taken shocks of 200 or 300,000 volts, no problem. No problem. Because there wasn't many coulombs of charge flowing through that shock. Versus, hey, if you lick your fingers and touch a car battery, you're going to feel it because that car battery is so big, it stores way more charges, even though they're at a lower height. It's the equivalent of someone dropping a 10-gallon or a 20-gallon bucket of water on your head from ceiling height versus dropping a drop of water on your head from the height of Mount Everest. That 10-gallon bucket of water from ceiling height is going to get your attention way more. Is that okay? That's a good way to think about voltage. Sort of how high an object is. We have been looking for a few days. Oh, actually, next thing I have for you is a take-home quiz. Let me give you that, because we have to fix a typo. Also, Courtney, also Lydia, today is a good day not just to have the yellow sheet out. You might want your blue sheet out. I'm going to give you a whole bunch of different ways to rewrite stuff based on the 6 equations that you have for electrostatics. You can record those on your blue sheet as your study guide. I just gave you all a take-home quiz. There's a glitch or a typo in the quiz in number 1. For some reason, when I hit print, the numbers didn't print properly. On my original, this is clearly a 5.0, and this is clearly a 3.0. So that is negative 5.0 microcoulombs, and that is positive 3.0 microcoulombs. Can you fix that on your quiz, please? Can you fix that on your quiz, please? Can you write that right now, Kareem? Right now? Why don't you have anything to write with? Okay, so fix that. By the way, what can I ask you if I give you 2 charges? Well, A, I can ask you to find the magnitude of the electrical force between 2 charges. I didn't ask for a direction. If I wanted the direction, I'd have to tell you which charge we were talking about, because each charge is going to feel a force in a different direction. Absolutely, part B, I could ask you to find the electric field when there's 2 charges. You'll find the electric field from charge 1, magnitude and direction. You'll find the electric field from charge 2, magnitude and direction, and you'll add them vectorially. I can ask you to find the electric potential at location A. Turn the page over. Suppose we have a fixed charge of magnitude negative 8 microcoulombs. How much work would it take to move an electron? Move what? Okay, it's an electron. That's your hint for some of the values that you'll be looking for. From an extremely large distance away, when I say extremely large distance away, what am I really talking about as a distance? Infinity, which makes one of your values, it's going to be much nicer, because we said out at infinity, there's a certain thing that happens out at infinity. To a final location 0.15 meters removed from charge Q1. Electron, negative or positive? Negative. And Q1, negative or positive? So these are like charges. Kareem, like charges? So you are going to have to do work to move that electron closer and closer. In fact, the closer you get, the more it's going to be pushing in the opposite direction. So you will have to do work. That's your hint for number 2. Number 3, a proton initially at rest, I would probably underline initially at rest, at point X will have what speed at point Y? John, what's this question asking you to find? Speed. Is it asking you to find work? So no. What's it asking you to find? Speed. If you turn your head sideways and imagine that up is sideways, is there a change in height? Is there a change in speed? Is there a yucky curvy force? That's a job for... That's your hint for that one. Okay? You'll get time later on in class to work on the quiz because today's lesson is short, but very nice. We have a problem. Well, not a problem. We have a yucky math situation. Kareem, up until now, we have been looking at little point charges, and we've noticed because the equation for force has an r squared on the bottom, as soon as you move anywhere, the force changes. And because the equation for electric field has an r squared on the bottom, as soon as you move anywhere, the electric field changes. And because of that, I can't use work equals force times distance. If I want to do anything with work, I had to go just like we did in gravity. Work equals the change in potential plus the change in kinetic. We had to go K, Q1, Q2 over R, and then ditto mark, ditto mark, ditto mark over R, just like we did in gravity. It would be wonderful if there was a nice, easy to set up situation where the force was constant, not changing. And so we could use good old work equals force times distance and use a bunch of other shortcuts. And there it is. It's called, the situation is called parallel plates. So I want you to imagine that you have 2 metal plates. You're going to set them up parallel to each other and a distance apart. They don't have to be as big as these 2 meter sticks that I'm holding up. In fact, the nice thing is, well, here's what I wrote. I wrote down another important problem is the parallel plates problem. Large flat metal plates. By large, Dylan, I mean, since all these charges are on the microscopic scale, large can be 4 or 5 centimeters long, large. Not 2 meters long or a meter long, large. Large relative to the size of the charges that you're dealing with. So if you take some large flat metal plates, you hook them up to a battery, and you charge them up using a power supply. You might recall from your Science 9 days that this is the circuitry symbol for a battery. The longer line was the positive side, the shorter line was the negative side. So if we take a battery or a cell, and we clip 2 parallel plates, 2 metal plates to it, one side will have a positive voltage, and the other side will have a negative voltage, or 0 if you just hook it up to the ground. Okay? So don't write this down, just watch. Supposing this was 450 volts and this was 0 volts, how many volts is there between these plates? What's the net voltage? If you traveled from here to here, how many volts would you travel through? Do the math, keep it simple, stupid, what? 450, okay? Sometimes, rather than having this hooked up to the ground, we'll charge this also positively, but not as positive. So because the bottom plate is 150 volts positive and the top plate is 450 volts positive, that bottom plate, relative to the top plate, is still negative, like relative to it. What would be the change in voltage that you would travel going from 150 to 450 in your head, please? 300 volts, okay. But usually you're going to see 99% of the time the negative plate will just be labeled with a 0, because the easiest way to do this is to hook the negative plate up to the ground. Okay? If the plates are very large, and again, by very large, I don't mean the size of meter sticks, I mean relative to the charges, even 5 or 6 centimeters. Here's the beauty, worth underlining. The voltage varies directly with the distance from the plates. Say, what? It's easier with numbers. Okay? I'm going to change one number here. Can you all look at example 1? It says, let's imagine that we have plates separated by, instead of 5 millimeters, let's make it 10 millimeters, just so we don't get the 5 and the 500 confused. So on your diagram right now, let's label this distance here as 10 millimeters. And we hook it up to a 500 volt battery. I figured that out by looking at the picture. Traveling from here to here, how many volts will I travel through? 500 volts, okay? I'm going to say the same thing. I want the same answer. Traveling from here to here, what's the potential difference? Okay, and this is now we're starting to talk about a difference in voltage, and that's going to become important. What if I went 5 centimeters of the distance? What if I went halfway? 250. That's the beauty of this system. The voltage, Matt, just varies linearly or directly. So, you ready? How many millimeters in total, Matt? Oh, I wrote 10 meters. Let me put an extra M there. Let's try that again. How many millimeters in total? So, 100 volts is how many millimeters in this setup? Every 2 millimeters is 100 volts. It's a nice linear relationship. I got 10 millimeters to play with. I got 500 volts to use up. That means this distance is 2 millimeters. This distance is 4 millimeters. I put an M again. This distance will be 6 millimeters, 8 millimeters, 10 millimeters. Okay? It's a nice linear relationship. Suppose we were to graph this data. What would the slope tell us? What I mean is, suppose we had a graph of voltage versus distance from the bottom plate. We could also do voltage versus distance from the top plate, but I'm going to go voltage versus distance from the bottom plate. It would look like this. It'd be a line. as opposed to the graph of voltage from a round circular point, which had a 1 over r, had an r in the bottom. That would look like this. It's a yucky, calculus-y, curvy graph. Ugh. Don't write that down, Prith, because I need more room here. Michael, can you read me this sentence?
What would the slope tell us?
I gave you some clever tricks for analyzing graphs, and we're going to use them. When I told you if they ever give you a new graph, and I've never given you a voltage versus distance graph, I've said if they want the slope, what could you try to figure out what the slope means? What can you do? What about the units? Divide them? Let's try that. In fact, you know what? I'll start out first of all by dividing the actual quantities. It would be volts per meter. I don't know what that is yet. So let's see if we can break it down further. So meters would be on the bottom. What's volts measured in if I break it down? This goes back to the very beginning discussion. How was voltage defined? As something per something. Okay, so a volt is a joule per coulomb. I'm going to put a dot between the C and the M so it doesn't look like centimeters, because you can't really tell that that's a capital C. And then I'd like all of you circle the J and the M. Believe it or not, that's something. What do I measure joules in? What do I measure in joules? Work. What do I measure in meters? Is there an equation that has distance and work in it? There is on your formula sheet. You got to go way back. In fact, it's Physics 11. Okay, Kareem, what was that? It's Kareem, sorry, Adeem. Blah, blah, blah. I'm tired. Now, I notice in our equation, we have the distance down there, yes? We have the joules on the top and the meters on the bottom. What is joules per meter the same as? So, you're telling me that volts divided by distance is the same as force. What do I measure force in? Per. Dylan, do you remember what newtons? I think it was you earlier that suggested newtons per coulomb. What did I say newtons per coulomb measures? Remember? Dylan, what? This is electric field. I don't know if you remember, I told you gravitational field is measured in newtons per kilogram or meters per second squared. I told you there was two ways to think about that 9.8. And then when I introduced electric field to you, I said it was newtons per coulomb or, and then I left a blank and I said you're going to find there's another way to think about it. You know what? Volts per meter is also electric field. Newtons per coulomb or volts per meter. And here's the beauty. This slope here, curvy or straight line? Can I use the math term? Constant or changing? We've just found a situation where we have a constant electric field, which is going to give us a constant force, which is going to let us use work equals force times distance again, oh thank God. Instead of the change in, final, minus initial, ditto mark, ditto mark, ditto mark, ditto mark. Also, although you don't know it yet, we're very close to inventing television. The old style of TV, not the modern flat HD screens, but if any of you recall having a TV that when you looked at it from the side, the front of the screen was curved, and then there was that big bulge in the back, that's an electron gun. Basically, you had an electron gun, you had a set of parallel plates, and that was enough to deflect electrons wherever you wanted to, and they would hit the screen and give you an image. We'll talk about how that works in a few days, but believe it or not, we're barely away from inventing the way TV used to work. So, for parallel plates, there's a constant ratio of drop over distance, and in fact, that's the electric field, voltage drop over distance. This ratio is the electric field, check, I've just proved that. And because the slope is linear, it means the electric field is uniform or constant. In fact, as an equation, and you can find this on your formula sheet, I think it says electric field is the change in voltage divided by the distance. I think this is middle row, second one over? Yes, I hope? Yeah. Now, there's a bit of a problem here because I cleverly told you one of the ways to figure out which equation to use was to look for if they gave you something in meters. This has meters in it, but wait a minute. So does that one. Has meters in it. I've picked my variables carefully. What does the letter R stand for? Radius. If they give you a round circular charge, think R, think radius, think circular, use KQ over R squared to calculate electric field. If they don't give you a round circular charge, if they give you plates and a voltage, that's why I'm using the letter D here very carefully, that's a distance. That's a distance. Okay? Which way would the electric field point? Which way do electric fields always point? All electric fields point from. That's how we define the direction of electric field. This you better memorize or write on your blue sheet, but not on your yellow sheet. Electric field is defined as which way a what would want to move if it could? A positive. So I guess the electric field, if I actually drew it in, would look like that. Draw a little line in the middle. We're going back to our notion of electric fields as lines. Remember the line pictures I showed you? You might also recall, don't write this down, I think we did for like a positive and a negative, and we had arrows going like this, or we could have like charges and the arrows were all kind of being repelled by each other. But I also told you that the closer the lines were together, the stronger the field. The further the lines were apart, the weaker the field. Remember that? Well, Kareem, I've just told you that the electric field in here is constant. So if you're going to draw the electric field between plates, they're first of all going to point from positive to negative. And they're all going to be parallel lines, all the same distance apart. Because that's how you would show a uniform electric field. So you can eyeball it. That there is the electric field between plates. Try and make each line the same distance apart. If you did this, Ryland, that would be considered incorrect because you clearly have, for some magic reason, a stronger electric field in the middle there, and that's not how parallel plates work. I would mark that wrong. Or if it was multiple choice, that would be a possible wrong answer to pick from. The only place this breaks down, Ethan, is near the ends. So if you want to, you could put a little curvy line there and a little curvy line there, and that right there explains why the old styles of TVs are blurrier than the new HD style. It's that little, there was always a bit of blur. Okay. It's more complicated than that, but it starts there. I know I haven't told you yet how this fits for television. I will. So the next way we have to calculate the electric field is it's the change in voltage over distance. So, example 2, find the electric field, magnitude, and direction inside the plates. Up until now, don't write this down, when I've said electric field, that's the equation that you've gone to. Matt, what letter is that on the bottom right there? I think radius, I think round circular things. I have plates here, don't use that one. What's the new equation for electric field? It's the change in voltage divided by the distance. Right? And I'm doing my little wings thing on the V so you know it's a voltage, not a velocity. Okay. What's the potential difference? What's the change in voltage between the plates? 225. What's the distance between the plates? 0.03. What's the electric field between the plates? Sorry? 7,500? Units. You could say newtons per coulomb. I'd give you full marks. But I think this time the better units to use would be volts per meter, because that's the equation that we used. And again, I'll give you full marks, Taylor, if you go with newtons per coulomb. That's fine. This would be more appropriate for this venue. Direction. Which way would a positive charge between the plates want to move if it could?
Towards the negative.
Or east, right, towards the negative? Yeah. Okay. You don't yet realize how much nicer this is going to make many of our standard situations about potential energy and kinetic energy and work. Our equations just became significantly cleaner, Hedrick. Besides the fact that this also not only is going to explain television, on Monday we will explain lightning. Serious. Okay. How does the electric field at the point X compare with the electric field at the point Y? Well, I think the first thing I'm going to do is I'm going to put a dot at the point X right there. I'm going to put a dot at the point Y right there. How does the electric field of those two locations compare? This is the theme so far of what we've been talking about. What's so nice about parallel plates? The electric field between them is what? Constant. So the electric field at location X and the electric field at location Y are the? Prove it. It says, explain your answer using principles of physics. I could do a fancy schmancy algebraic proof. I think I'm just going to crunch the numbers. I'm going to draw a little line down the middle. I'm going to find the electric field at location X. I'm going to find the electric field at location Y. Now, electric field at location X is not going to be KQ1 over R squared. I'm between plates. It's going to be the voltage at location X divided by the distance at location X. So you ready to put everything together? Marcus, I'm going to pick on you. You ready? How far from here to here? Good. How many volts from here to here?
500.
So each centimeter is how many volts?
100.
Yeah. So you ready? How many centimeters to put location X? So 0.02 if I go to meters. How many volts if I start here and end up at location X have I traveled through? Yep. What's the electric field at location X? That 10,000? Double check me, but I think it's 10,000, yeah. 200 divided by 0.02, I'm pretty sure it's 10,000. Yes, Court, yeah. Okay, 10,000. And again, you can say newtons per coulomb. This time, Brian, I would go volts per meter. Ethan, let's do the second one. Okay. How far from here to location Y? So 0.05. How many volts have I traveled through? Gee, do you also get 10,000 when you divide? Yes. So there's my proof. Good enough. I could probably have done a lovely algebraic thing, but here I think it was just easier. Plug and chug both of them, and they're the same. And that would work for any location. Rylan, if you were at 3 centimeters, it'd be 300 divided by 0.03. If you were at 4.5 centimeters, it'd be 450 divided by 4.5. That's the beauty of the fact that A, voltage progresses linearly between the plates, and because of that, B, we get a constant electric field. How does the electric field at point X compare with the field at point Y? We already did part A, so part A we already said they are the same. What about diagram B? Is the electric field at location X the same as the electric field at location Y?
Yeah.
Someone said yes, someone said no. Convince me. How do you calculate electric field for from point charges. And here's the key. Listen to what I said. How do you calculate electric field from point charges? A point is a circle. Ethan, on your formula sheet, which by now you should have in front of you because I've told you to get it out several times, right?
Yeah.
Can you find for me the electric field equation for a point charge? And for a point charge, you're looking for the electric field equation that has the letter R in it.
You want the electric? Which one was it you said?
Look up.
Field charge.
Electric field for a point charge. For those of you on YouTube, this is my fun class. It's all good. Take a stab. Seriously, this is how we learn. Go ahead. Read something.
F equals.
Not F equals, because I don't want to find the force. Okay? I think it's on that line, though. Pardon me?
E equals.
Nope, can't be volt. Look up, please. Please look up. This electric field is voltage over distance because this is a distance. Look up, Ethan. Point charges look like what shape? So find the equation for electric field with R in it. Yes, and that's how you can figure it out if you blank out. KQ over what?
R squared.
Thank you. Over what?
R squared.
And one more time, not to make fun of you, but this is the whole point. Over R squared, that means that this and this can't be the same. Which one's bigger? The electric field at location X or the electric field at location Y? X, because closer in, dividing by a smaller number, you're going to get a bigger electric field. In fact, this is that inverse square thing, Lydia, that we've seen occasionally with the squared in the denominator. I think if you go twice as far away, you're 4 times weaker. If you go 3 times as far away, you're 9 times weaker. Is that okay? It says explain your answer using principles of physics. Changing R leads to a changing electric field. I'll bring in a vector above there somehow. Really, it's a changing R squared. The first part, showing that they're the same, Dylan, I'm going to argue I just proved that, so I'm not going to reprove it. That's okay? You have some space at the bottom here? Ready? Here are some consequences of that. Ethan, coming back to you on the formula sheet, can you read me the equation that has force F and capital E electric field in it?
E equals F over Q.
Can you get the F by itself, please? Yep.
Equals E times Q.
And I'm going to write it as Q times E, just because I kind of want it to look like mg for gravity, where m is the mass, Q behaves an awful lot like mass. Okay? Except, Kareem, between plates, what did we just say the electric field could be calculated as?
Do you have that? No. Between plates?
There's yet another way to find electric force. Charge times voltage divided by distance, which honestly is pretty plug and chug. Now that's going to find you the force on a little charge that's stuck between plates. Okay. That also means, since work equals force times distance, I guess work equals Q V over D times distance. What do you notice, Prith?
These cancel.
We've just, bring that back. Let me bring that back. When we did potential energy, I already showed you that was your equation where we defined voltage, I think says energy divided by Q. If you get the energy by itself, you get the QV there. I've just told you that is a shortcut for work. And it works really nice between plates. Really nice. I'm going to go technical on you. We can see why, by the way, in the graph that I drew with you folks, I started at the negative voltage and moved to the positive voltage. In this graph, we're starting at the positive voltage and moving to the negative voltage. And later on, when we do circuits, you're going to see that's the preferred way to do it. I didn't want to scare you right away with a negative graph. We can see why the electric field is constant and why it varies from a point charge if we graph them. The equation here for electric field is voltage over D. Really, what we're saying is voltage equals electric field times distance. It gives you a lovely y equals mx straight line. Here, electric field is kq over r. You've got an r in the denominator. Of course you're going to get this. R squared in the denominator. And if we wanted to look at voltage, voltage would be kq over r. That was the one I could also have written. You're going to get a yucky reciprocal graph no matter what prith. You're not going to get a lovely straight line. Okay? Who remembers the opening statement, the thought problem, where I talked about why is it that when you get a shock from a 100-volt battery it hurts, but when you touch a 10,000-volt balloon it doesn't hurt? What was the analogy that I gave you for voltage? What did I say you could think of voltage as sort of behaving like? Height. So here's the rant. A technical comment. For all electricity concepts so far, I've tried to connect it to gravity because that's what you're familiar with. What would be the gravitational analogy for voltage? Put the dice down, Ethan. Thank you. Well, voltage is energy per charge. If I go to gravity, that would be energy per mass. And if I replace potential energy with mgh, I get mgh over m. What happens to the m's? And I get gh. It's not a perfect analogy. Voltage isn't exactly like height. It's more like height times the strength of the gravitational field. But you know what, Adim? You can just pretend voltage behaves an awful lot like height. If a charge has a higher voltage, you can imagine that it started rolling down a higher hill towards me. If it has a lower voltage, it started rolling from a lower hill towards me. The amount of charge is what does the damage. Again, if you had a massive hill and you rolled a little ping pong ball towards me, wouldn't worry me at all, even if it was a hill that was 100,000 meters high, 100,000 volts, no problem. That ping pong ball, when it hit me, nothing. If you put a bowling ball on a 20-meter hill, bowling ball having more mass, more charge, and you rolled that towards me, well, now I'm already nervous. So it's not voltage that does the damage, it's the amount of charge. It's current, which we'll look at next unit, because current is how many charge every second you're absorbing. Okay? What's your homework? 1, 2, 3, 4, 5, 6. In question number 4, what are they asking you to find? You can't use K, Q1, Q2 over, use that other version, I think, of force that I gave you. Take the force with the electric field equation in it and combine it with the electric field for plates equation, and you'll get the new equation for force. Okay? Question 5, what are they asking me to find?
Work.
Don't go K, Q1, Q2 over R. You don't have two charges. You know what? I think there's another variation of work that I gave you as well. Okay? You also have a take-home quiz. Put your pencils down, please.